So Manoj is an associate professor at the Biological Systems Engineering Department at WSU, and he is going to be talking about the use of cyber-physical systems in the AI and robotics for agriculture.
Okay, good afternoon, everybody. This is Manoj Karkee again, associate professor in the Biological Systems Engineering Department and Center for Precision and Automated Agricultural Systems at Washington State University. As mentioned, I'll be talking briefly about some of the applications that we are working on that utilize AI, CPS, and robotic technologies to solve some of the challenging practical applications in agriculture. And I'll also try to briefly present my thoughts around what the opportunities and challenges are in this space of what we also call smart farming. So first, let me briefly introduce what we have done in the past and how it is transforming into this is what we call the smart ag that is supported by or empowered by AI. So we have been over the past century or so developing many different kinds of mechanization solutions for agriculture, such as combine harvesters and things like that. In recent decades, we have also been successful in developing and adopting automation technologies such as auto guidance systems that operate with the GPS, RTK GPS to be exact, technologies to automatically follow specific paths or go around the field in straight lines or whatever paths we define, and many other robotic solutions such as the ones used for crop thinning and things like that. These technologies are also working together with what we call precision crop management systems that have both softer and harder technologies to identify the needs of specific plots or specific areas in the field and manage those fields at different precision level to achieve the desired yield and quality parameters, or to achieve desired input applications in those specific fields. This is all supported by the technologies that we discussed or mentioned rather earlier, including artificial intelligence, robotics, and cyber-physical systems, which is empowering us to what we call achieve more better quality of products with optimal amount of input. But also, I believe this has to occur without compromising our capability in the future to achieve the same. And I believe artificial intelligence and other technologies, again, would help us achieve this goal. In this particular slide, I would like to briefly kind of introduce the interaction between these components that we have been mentioning, including AI, CPS, and robotics. But what does it do for us is that it provides capability to make and implement farming decisions with increasingly better or desirable outcomes over time. So on our left is the artificial intelligence tools and techniques, more the fundamentals of AI. On the top, I have bubbled CPS, our physical system there, which includes, again, as we know, the interconnections between various components that are used in farming, both the farming systems, animal and crop systems, various kinds of sensors, various kinds of machines, various kinds of decision support tools, all connected together, and through the support of artificial intelligence and other technologies, helping us achieve what we want to achieve again in agriculture. So how do they interact? The fundamental tools and techniques available with AI are used to develop technologies that are applicable in farming that include pattern recognition, machine vision, big data analytics, decision support systems, as well as robotic systems. And these technologies would then help us do various things in farming that will help us get, again, to or achieve the goal that I mentioned earlier. These particular tools include perceiving plant or animal conditions and environments. What are the stresses associated with a given crop or given animal or animal production system, how they're doing, what are the needs. Then using that kind of information, we'll be able to make farming decisions, apply certain kinds of inputs, intervene with the animal health, whatever else we would like to do. Implement these decisions in the field. If it is a decision to apply a certain amount of water at a certain time, can we do that automatically in the field? And then analyze the outcome. What happens after we implement our decisions in farming that are supported by AI and other techniques, as I'm describing here? What happens and how does that help us be better in the future? That's the analyzing part of it. So with these technologies and tools, and then we'll be able to improve water and nutrient management systems, pest management systems, canopy management systems, harvest and post-harvest operations, and for that matter, anything and everything we do in farming could benefit from the interactions between these technologies. And that helps achieve, again, our ideal goal of understanding and managing variabilities, hopefully at an individual plant or animal level. In this slide, I would like to kind of sum up what I described and kind of present the promises that, that I believe we have in going into the future, based on the capabilities and the power that we have gotten through these, again, AI-based and other technologies we described in the previous slide. Enable efficient agriculture at all scales and locations. What does that mean is that I believe we are getting into the future that would benefit from the technologies in a way that can be applicable to both the small farms as well as big farms. For example, tools that we could generate using AI-based, let's say, deep learning and other analytic tools and big data analytics that we do should be applicable to some extent to smaller farms as well, in addition to large farms. And I believe this would be applicable not just in West and North, but also in the agricultural industries in developing countries in South and East. Sustained human experience and knowledge. Farming relies heavily on human expertise right now. Farmers gain experiences and use that experience over decades and decades of their involvement in farming. I believe with AI-enabled technologies, we would be able to sustain these kinds of knowledge and experience through collaborations between human and these AI-based systems, so that AI would learn from human experiences. The human would get help or support or decision support systems from the AI-based techniques, and then this collaboration would lead us to a situation where experience that experts and farmers have now would be applicable in the next generation in the future. I think that transition of experience would be enabled by these kinds of technologies. Facilitate consistency, reliability, and repeatability of farming processes and operations. Because we are working in this kind of collaborative environment with AI and human, I think what happens in the field becomes much more consistent, because we're not relying only on experience of one specific farmer or manager. Rather, we are expanding it to other experiences of others and then the tools that are available. So I think it will help us be more reliable, consistent, and repeatable over time. Improve socioeconomic and environmental sustainability. I believe we can apply less to produce more. That also helps to improve the environmental sustainability of farming operations. With these kind of high-level discussions, I'd like to briefly introduce a few specific projects that I have been working on at Washington State University in the last like 10 years or so. One of those projects is around automating cherry harvesting systems. We've been using big machines and shaking cherries off of the trees. These are mechanical systems, and we're further improving what they are, but also aiding machine vision systems with different kinds of image processing techniques. Certainly in many of these applications, I may or may not explicitly mention that this as we discussed, but often we are using different kinds of deep learning technologies with the adoption that makes these application in these kinds of situations more efficient and accurate. Anyway, one of those is to automate cherry harvesting systems with the machine vision system. We have developed camera systems that work in both day and nighttime conditions, take images, and then we analyze them in certain ways so that we can identify and locate these branches, even under the situations when these branches are partially or sometimes even very heavily occluded or blocked by leaves and fruit. Using various clues and the AI-supported tools, we can still very reliably estimate their locations, and then we can use a robotic system to get to those branches and shake the cherries off. Next is a project that we've been working on in robotic apple harvesting. Again, as you can see in these videos, we use different kinds of learning techniques to identify, locate, get to those apples, and then detach them from these stems, from the branches, and then collect them onto something. The one on our right is a full-scale machine that was developed in collaboration with the company, because this company developed this full-scale machine. With our collaboration, we provided a lot of our expertise in doing so. This machine has 12 amps, 6 in each side of the machine, and they operate in parallel to pick apples and convey them or transport them onto a container bin. This video we saw on our left was showing different versions of the prototypes we developed in our lab before we started collaborating with FF Robotics in developing the full-scale machine. Next, we have also been working in many other robotic AI-powered robotic systems in agriculture, including those ones for robotic pruning, pollination, and thinning in fruit crops. As we can see in these images here, farming environment is quite complex, and we have to deal with uncertain and variable lighting conditions. We tend to minimize these the effect of these challenging situations by using synchronized artificial lights, both in day and nighttime conditions, using some specialized cameras, and again, then using deep learning based and other algorithms in achieving what we like to achieve. That includes recreating 3D environment, estimating various canopy parameters, such as how many fruit are there, where they are, how many flowers and flower clusters are there, where they are, how the branches are oriented, and how do they relate to each other. All those parameters then can be applicable in developing robotic solutions, for example, for pollinating these crops, pruning specific branches every year, thinning certain flowers, and so on. In this specific video here, we see an example, a slowed down video that shows the capability of a robotic system that can identify these branches for pruning and get to those branches and automatically prune them off. This was tested in a mock-up system in the laboratory, but shows the capability of what we can do. and similar systems are being developed for thinning and pollination as well in our lab. Again, a lot of these projects are being conducted in collaborations with the scientists at WSU, Carnegie Mellon University, Oregon State University, and Pennsylvania State University. I don't want to go into details there and name the names, but I'm really happy to have these collaborations. And thank you, all of you, if you are here in this conference or the workshop. Thank you for your collaboration. We are also working in robotic weeding systems for vegetable crops. Briefly here, you can see we can differentiate different kinds of crops and weeds, for example, carrots and onion, and the weeds that are present in these fields, specifically in our area here. And we are developing small robotic vehicles to apply chemicals precisely on top of these weeds and keep the plants that we want to keep safe. With that, I want to spend another minute or two on just talking about a few specific challenges and opportunities I believe we have in this smart AI-empowered agriculture. And then there will be time for questions, if there is time for me. One of the challenges we face in agriculture often is related to how we use a lot of different kinds of data we collect, which is increasingly a case in recent years. We are using IoT devices and many different kinds of sensors connected to these cyber-physical systems, collecting many different kinds of data, both image data and non-image data. We are able to use those data to get certain information that is useful in making farming decisions, helping farmers do certain things better. But I think there is still room for converting this data into actionable information that is, again, more valuable in all kinds of situations in farming. Another I mentioned earlier was an area I'm interested in, and I think where AI-based systems help us achieve would be to understand the needs of individual plants or animals in farming, find the variabilities, understand their needs, and apply input at right time, at right location, and at right rate. Finally, I think this will be the slide, the second last slide. I think with these AI-empowered tools and technologies, we have an opportunity to develop tools and technologies that are accessible for farmers all around the world. Cell phone-based devices, if we can come up with cell phone-based applications, rather, if we can come up with some applications that are useful for farmers, I think it will be applicable for all farmers all around the world, as the cell phone-based technology is accessible to those farmers quite easily. Similarly, smaller modular robots can be applicable to wide different kinds of farmers around the world. Egg control center is another concept I believe we need to look into and work in the or focus in the future, where AI, virtual reality, and augmented reality would allow us to make farmers less and less dependent on labor being in the farm, in the field, and manage these farms more from a remote location like our offices. With that, thank you very much. I'm not sure if I took much longer than I was given, but this is what I have.
No, you did not use more time, Manoj. Thank you very much for this wonderful presentation. I saw one question and I would like to take it up. And this question came from Mike, and he is wondering if any of the solutions that you surveyed through are used in the ag industry. Are they in use by the ag industry is the question, if you want to comment on it.
Well, thank you very much. In our lab and at the Center for Precision and Automated Agricultural Systems that have about 15, 16 faculty members involved and are working together in developing these kinds of solutions. A couple of us are here in this call as well, or in this workshop as well. I think Dr. Chin Zhang is there, Dr. Lofcourt is there, Dr. Sindhu Sankaran perhaps is also there. We are working together in developing many different kinds of solutions in addition to what we saw here. Some of them have been adopted to some extent. For example, we have developed some precision chemical application systems. We have developed some handheld devices that workers could use to improve their work efficiency in orchards. And then some of these newer technologies that are much more, in a way, require technologies to be integrated in a relatively more sophisticated way. As you saw, our robotic apple harvesting system is being developed and tested with a potential commercialization in recent future. And there are other technologies also. We're trying to work with some other startups and other companies to hopefully make them commercially adaptable. One example would be cell phone-based fruit counting. There are other cell phone-based technologies as well being developed at our center. These have kind of a potential direction that might lead to commercial adoption in recent future. The hardware-based technologies, these sophisticated robotic machines would take much longer, as we all know, but at least we're making some headways with robotic apple picking, and it's likely that it will be commercially available in the next few years.